So welcome back, everybody. You came back, I'm glad. So our goal is to figure out how to make more baryons and antibaryons. And if you recall, we have three conditions. The first is baryon number violation. The second is C and CP violation. And the third is departure from thermodynamic equilibrium in the early universe. So I covered baryon number violation in the standard model yesterday, and today I want to get to C and CP violation and departure from equilibrium in the early universe, and then try to illustrate these with a particular mechanism of baryogenesis called leptogenesis. So we have baryon number violation, and let me get back to C and CP violation. So if you recall, C acts on a typical complex scalar field by phi to phi star. And this corresponds to exchanging the creation operators for particles versus antiparticles in a theory where you have some kind of conserved U1 where it makes sense to talk about a particle and distinct antiparticle. On fermions, or at least on a Dirac fermion, my Dirac fermion gets mapped to what I call gamma C psi bar transpose, where gamma C is minus I gamma 2 gamma 0. So what's going on here is in your minimal free theory of a Dirac fermion, you have a notion of a particle and an antiparticle, and you have creation operators for each. And now you want to flip those creation operators. But when you look at the field comes along with all kinds of spinor junk. And in order to flip the spinor junk in a way that preserves spin between exchanging a particle and its antiparticle, you get this extra gamma 2 gamma 0. And it all works there. And finally, at least if you want to specialize to something like QED, the vector field picks up a sign. And the reason the vector field picks up a sign is motivated by QED in that you have J mu, A mu is your basic interaction, where J mu is the conserved charge current. And this J mu, the contribution from a Dirac fermion is going to be psi bar gamma mu psi from a complex scalar charged under, let's say, an abelian gauge theory is going to be phi star d mu psi, phi d mu psi. And either way, when you apply these transformations, these things pick up a sign under C transformations. And this is what you'd expect. When you flip a particle and an antiparticle, the effective sign should change, and that corresponds to the sign of the current changing. So to compensate for that, if you want C to be a symmetry of QED, you also have to assign A mu goes to minus A mu when you do this transformation. Now you can also extend this to QCD. For QCD, you have to be a little bit fancier in that you also have to worry about the adjoint index. And the sign you get for the gluon, I won't go into it, but the sign you get for the gluon depends on what happens to the corresponding generator under transposition. So this is something I'll let you work out for yourself. But in any case, we have this well-defined set of C transformations for theories with complex scalars, Dirac fermions, and vector fields, whether abelian or not abelian. But we want to look at the standard model. And the standard model doesn't have Dirac fields. At the fundamental level, it has vial fields. It has two-component fermions, and specifically two-component fermion representations of SU2 left and U1 that aren't matched by corresponding opposite representations under the same group. So to get an idea of what happens with chiral fermions, let's just take our Dirac fermion and decompose it into left and right-handed components. So I'll do my usual thing, psi, and in the chiral basis, I split it into psi left, psi right. I should add that this particular form of the charge conjugation operator applies specifically in the chiral basis. if you use a different basis for your gamma matrices for some reason, the specific expression you'll get here will be different. So I'm implicitly using the chiral basis for Dirac matrices. But as long as I stick to the chiral basis, I'm fine. And in the chiral basis, I have this split into left and right-handed components. And the split into left and right-handed components is motivated by the fact that under Lorentz transformations, under the minimal irreducible Lorentz transformations, psi left transforms into itself, psi right transforms into itself, and these things don't mix. The reason for assembling a Dirac fermion is the mass terms you write down, at least for the standard model fermions, link the psi left and psi right through a mass term, and writing 4-component Dirac fermions, even though they're not irreducible representations Lorentz, is just sort of a quick and dirty way, sneaky way to diagonalize your mass matrices. But in any case, if I look at this and I apply C to it, it's just a matter of decomposing this matrix acting on this. And the result of decomposing this matrix on this, and okay, so I'll remind you that gamma mu in the chiral basis is sigma mu, sigma bar mu, where sigma mu is the matrix 1 and the Pauli sigma matrix, and sigma bar, I just put a minus sign here. Standard stuff. When I apply a C transformation to this, with this form in the chiral basis, what you find is psi left goes to I sigma 2, psi right star, and psi right goes to, I think it's a minus sign, yeah, a minus I sigma 2, psi star left. And if we think about the standard model, this is a mess. This is a problem. And this is a problem because the things I assemble into a Dirac fermion in the standard model come from different representations under the underlying electroweak gauge group. So for example, the left-handed parts of the fermions come from electroweak doublets, and the right-handed pieces come from electroweak singlets. So the left and right-handed pieces have different gauge transformations under the underlying standard model gauge group. And that means that transforming one into the other, because they have different gauge representations, is ludicrous. It's something you don't want to do. And in this sense, if I try to extend my C transformations to these chiral fermions in the standard model, it just doesn't make sense. So I could try to get around this. I could try to get around this by saying, okay, let me try to redefine C where these things don't transform, but that doesn't reproduce the C invariance I would have for QED or QCD. So in this sense, even though we have a C invariance for QED and QCD, it doesn't extend to the full standard model gauge group. So in this sense, we have C violation within the standard model, and this is good. We check off this box for baryogenesis requirements. The second bit here, though, is CP violation. And P is just parity, and CP is just charge conjugation and parity. So if you recall, parity is just T goes to T, X goes to minus X. So you just flip all the spatial stuff. Under this, a phi of Tx goes to phi of T minus X. So there's no phi star stuff. For a Dirac fermion, psi of Tx goes to, let me double check this. It's a gamma 0, but I want to make sure I get the gamma 0 in the right place. And A mu goes to what I'll call eta of mu, or minus eta of mu, eta A mu, where eta 0 is minus 1, and eta for the spatial components is plus 1. So this is just a fancy way of saying that the spatial components of the vector field transform like a vector, and the time component doesn't change under parity, in the same way that we have here. So first of all, if I take this transformation and I apply it to the chiral components, what you find is effectively psi left goes to psi right goes to psi left, so parity is no good in the standard model, for the same reason that C is no good in the standard model. But if I take parity and I combine it with C, I end up doing kind of the bad thing twice. What I mean by this is C conjugation takes left to right, but the parity transformation also takes left to right. So if I go left to right and right to left, I get back left to left, and I'm good to go. So lumping this together, it turns out that when I combine C and P, each of which are no good with the standard model. Okay, I'm going to have to erase my lovely Sahara. Actually, maybe I'll just flip the board. Maybe I won't flip the board. Well, let's find out. I think this is more trouble than it's worth. Okay. Okay. I don't need to fully crank it down. Okay, so I'll just... Okay, I hope that's high enough. So if I go to CP, going to CP, CP is pretty straightforward. My phi of t of x goes to phi star t of minus x. So that's straightforward. My psi of t of x turns out to transform, when I lump all this stuff together, into a, again, let me go and make sure I have this thing right, a minus gamma c, psi star t minus x. And, okay, I won't do the vector transformation, but the vector transformation is the two minus signs cancel, and I'm just left with the eta mu bit. Here. Okay, so I've got my parity, I've got my C and my CP. And the reason CP is better behaved than C or P individually is if I look at the chiral components of this implies that psi left goes to, make sure, double check that. Okay, I think I've got all my signs right. So CP together is well behaved with respect to the gauge symmetries, in the sense that it's transforming a representation of the gauge symmetry into something that is essentially the same representation of the gauge symmetry up to the conjugation. And the upshot of this is I can go and write down terms of my Lagrangian with the full electroweak interaction of structure. And for the most part, these terms in my Lagrangian are going to respect CP altogether. Now, there's going to be one exception. I'll get to that in a second. But at least CP has a potential of being a good symmetry of the standard model, just given the gauge structure and the fermion representations. So let me give a couple of examples. So my first example is the simplest gauge representation we have in the standard model, which is the right-handed electron. And the Lagrangian term I'll have here is simply this. So I've got my usual derivative term, and then I have the covariant derivative, but because my right-handed electron is only charged under hypercharge, it's not charged under SU2 or SU3, I just have the hypercharged gauge field. And sit down, you work through all these transformations, flip the x signs, then go back to your action, flip your x variable back, and ultimately, at the end of the day, this thing ends up transforming in the action to exactly the same thing you started with. So this piece, this gauge kinetic piece for the right-hand electron works. You can show that all the gauge boson kinetic terms are perfectly fine. They transform into themselves. They're invariant under CP. The one thing you have to worry about, though, is the Yukawa couplings. So the structure of a Yukawa coupling. So here's one example. Yu, Ij. Let me try to get my indices right. I have my left-handed quark And here I and j are flavor indices, so they run over the generations. So we've got q bar, li, I got my Higgs field, and I have my urj, and this comes along with its Hermitian conjugate. Yu dagger, ij, u bar I, h dagger, qi. I think I've got I have my indices right. So it turns out when I take this and you apply the C transformations to it, what happens more or less is this term transforms into this term, and this term transforms into this term, but the couplings don't do anything. So what I get at the end of the day is, because this term transforms into this term, and then I flip these, I end up with essentially a yu star. So in other words, the transformed form of this turns out to be yu star, ij, q bar li, h urj, plus yu star, dagger ji, u bar j, h dagger qi. So under a CP transformation, I almost get back what I started with. Except my coupling has now picked up a complex conjugation. So CP would definitely be a symmetry of the standard model if the Yukawa couplings I started with in this so-called gauge eigenstate basis were all real. But there's no reason for them to be real. And in fact, we have experimental evidence that they aren't real. And the fact that they aren't real within the standard model of 3 generations leads to CP violation. So I should warn you, though, just because you have okay, so well, let me say 2 things. First of all, CP violation, at least the normalizable level, usually corresponds to having complex couplings within your Lagrangian. And what typically happens is you have your operator transforms into itself up to conjugation of the corresponding coupling. So in most cases, what most cases we'll see, CP violation comes from having complex couplings in your Lagrangian. But having complex couplings in your Lagrangian isn't sufficient for CP violation. So just because you write down a theory with a complex coupling, it doesn't necessarily mean you have CP violation. So a simple example of a theory that doesn't have CP violation is, okay, in analogy to this, suppose I have a complex scalar with a Yukawa coupling between some complex scalar and some pair of fermions, psi and chi, and I've got their Hermitian conjugate, and I allow this Y coupling to be complex. What I can do is change my field variables. I can change my field variables. So let's say if Y is equal to some modulus e to the I alpha for some phase, I can change my field variables chi to chi e to the minus I gamma, and that field, in terms of these new field variables, chi with the extra phase, this thing cancels off this, and my Y becomes real, and the theory ends up being invariant under CP. So the point I want to make is having a complex coupling doesn't necessarily mean you have CP violation. You need to have enough couplings in your theory that you can't get rid of the phases in the couplings by making field redefinitions, field transformations. And it turns out that within the standard model, you need at least 3 generations to get a physical phase within the Yukawa couplings that you can't get rid of by field redefinitions. So there's a counting you can do. Roughly what happens is the more generations you have, the larger the dimension of these Yukawa matrices. And the larger the dimension of the Yukawa matrices, the more possibilities for complex couplings you have. And it turns out that the number of complex couplings within the Yukawa matrices increases faster with the number of generations than the number of fields you have. And when you go through, sit down and count the number of couplings, it turns out you need at least 3 generations within the standard model to have physical CP violation. And this physical CP violation comes out in a single physical complex phase within the CKM mixing matrix, the Kabibo-Kobayashi-Maskawa mixing matrix. So the standard model has CP violation precisely because we know it has 3 generations. And because it has 3 generations, there are enough independent complex couplings that even after you sit down and make all kinds of field radar definitions, you're stuck with at least one stuck with one complex phase at the end of the day, and this signals CP violation. This means that when you do these transformations, even if you're really clever about your field variables you choose, you're still stuck with something that's non-invariant. So CP violation is a bit more subtle within the standard model. It's a bit more subtle, but it turns out that the CKM phase breaks CP explicitly as well within the standard model. Now, okay, this is a bit off topic, but I can't resist. It turns out that there's an extra term you can write down in the standard model Lagrangian that does violate CP. And this term that violates CP has a form of this. So, I forgot the all-important tilde. So this should look familiar. This looks a lot like this anomaly term we worried about for SU2 and U1, but now that it applies specifically to the standard model gluon fields. And it comes about, so there's a way to understand it coming about from the same wavy structure of the non-abelian gauge theory vacuum, in this case the SU3 gauge theory vacuum. And it turns out that when you take into account that classical vacuum structure, and you take an appropriate linear combination to get the proper quantum mechanical vacuum, it generates this effective term in your Lagrangian. So this is an allowed term in the standard model Lagrangian. And if you sit down and work through your CP transformations, it turns out that this thing goes to minus itself under CP. So this thing is CP violating. And it's actually a bit of a puzzle. And it's a puzzle, okay, I'm getting off topic, but okay, again, I can't resist. It's a bit of a puzzle because this operator, when you connect it into an effective theory of mesons and hadrons at low energies after confinement, this operator gives rise to electric dipole moments for the neutron. So it predicts an electric dipole moment for the neutron. Electric dipole moments, at least permanent electric dipole moments, are CP violating. And with a permanent electric dipole moment, it's CP violating. People have looked really hard to find it, and they haven't found anything. And the result is the theta parameter has to be less than about 10 to the minus 10 based on current experimental results. On the other hand, the allowed range of the theta parameter is somewhere between 0 and 2 pi. So this is a puzzle. It's a puzzle that goes by the name of the strong CP problem. And the puzzle is that if I just have some random parameter I can write down in my Lagrangian that can be anywhere kind of order 1, why should it be, why should it have to be so tiny? And there are lots of interesting ideas behind ways to make this tiny. One is something called the axion, which I think you'll hear about from Andreas Wingwald. But anyway, it's an interesting problem or interesting puzzle within the standard model that the standard model doesn't address. Now, I should also add that you may be wondering why we don't have a similar theta term for the SU3 part. So I can think of this as a theta 3. You could also imagine a theta 2 term. And it turns out that the theta 2 term is unphysical. It's not observable, precisely because you have this B plus L anomaly within the standard model. So what you can do within the standard model is it turns out that when you make a transformation by an anomalous symmetry, you end up shifting the value of this effective theta parameter. So what you can do within the standard model is do a B plus L transformation and use that to set the SU2 theta parameter to 0 without changing the rest of the Lagrangian. And that means that the corresponding SU2 theta parameter is not observable. Okay, anyway, so again, this is a bit of an aside, but it's sort of a fun aside that connects a bit to what I spoke about yesterday. Okay, but in any case, the end of the story is that we have C and CP violation within the standard model. The CP violation comes from the phase in the CKM matrix related to the complexity or the non-reducible complexity of the Yukawa matrices. So this satisfies my second Sakharov condition. And now I want to go to the third Sakharov condition, which is departure from thermodynamic equilibrium, and specifically departure from thermodynamic equilibrium within the early universe. So for this, I'm going to remind you of a few things that Matthias has either covered or probably will cover, but I want to talk about them in a slightly different way than he'll probably talk about them. So the third thing is we need departure from thermodynamic equilibrium. And in fact, we are guaranteed some degree of departure from thermodynamic equilibrium simply from the fact that our universe isn't static. Our universe is expanding, is changing in time, whereas a system in full equilibrium just sits there and hangs out and doesn't change. So the fact that we have an expanding universe with scale factor A of t, and specifically a non-zero time derivative of AAT, expanding universe, means that we have a non-equilibrium. So this is speaking formally. In practice, though, it turns out that for a lot of the history of the universe, the rate of expansion of the universe was really slow compared to the time scale of the processes that tend to drive the universe to equilibrium. And what this ends up meaning is that even though the universe is not technically in equilibrium, it's almost in equilibrium in an adiabatic sense, in that for a lot of the evolution of the universe, the expansion can be treated adiabatically in that you have essentially an equilibrium system with a temperature and possibly chemical potentials that are changing very slowly, and it looks like you have an equilibrium distribution at any given point of time where the parameters of that equilibrium distribution just change along pretty smoothly. So the upshot of this is, okay, on one hand, this is good, in that if we had violent non-equilibrium in the early universe, we'd have a much harder time describing it than if it's adiabatic. The second thing, though, is because we have very close to equilibrium, for a large chunk of the history of the universe, you can describe particle phase spaces, as long as they're fairly weakly interacting, by very simple distribution functions of a familiar form. So these simple distribution functions, and this is for a particle species I'll call I. So like I could be an electron or muon or a photon or something. And the form of these is just the usual Bose-Einstein or Fermi-Dirac distribution. So here, beta is 1 over t, the usual thing. The plus sign is for fermions, the minus sign is for bosons. And the mu, I should put an I on this here, the mu is a chemical potential. And finally, the E is a relativistic energy. So for a good chunk of the evolution of the universe, I can describe particle densities through these very simple, well-known distribution functions, Bose-Einstein or Fermi-Dirac, where the only thing I have to take into account that's not technically at equilibrium is that t is now some function of t, and my chemical potential is a function of t. But these tend very often to just evolve essentially adiabatically very slowly. So you track equilibrium in this sense, except up to the fact that you have very slow link parameters within your distributions.
I have a question. What should set the scale for the relaxation time? I mean,
I'll get to that. Yeah, but it's Hubble, it turns out. Okay, so we have these distribution functions, and what you do with distribution functions is calculate thermal expectation values. So these are distribution functions with respect to momentum. So for species I, we have a number density that you derive from the thermal distribution function, and it's given by, let me write this and explain it. So for the number density, as a function of for a given temperature and chemical potential, I just take my distribution function and sum it over all the possible states of the system. And in this case, I'm treating my states within my system as essentially free particles. So this is a good approximation as long as everything's weakly coupled. So I've got my weakly coupled particles that I'm treating with these distribution functions. I take my distribution function, I take this form, plug it in here, and Okay, I'm not going to compute the exact integral, but you can compute the approximate integral in two useful limits. So the two useful limits are either that the mass is big compared to the temperature, or the mass is small compared to the temperature. So the mass is small compared to the temperature turns out to give you a zeta 3 over pi squared gi t cubed. So this is t much, much greater than mi or mu I. So actually, this was a question yesterday. I said that number densities in the early universe go like t cubed. This is precisely the t cubed dependence. So if my temperature is really big compared to the mass of a particle, you don't care about the mass anymore, and this is just what you're left with for the number density in a leading order in the expansion in essentially t over m or t over mu. So this is great. I should also mention that gi is a number of internal degrees of freedom. So things like colors or spins or what have you. Now, in the opposite limit, I forgot one thing. I think I call this psi in my notes. Or I guess psi n. Sorry, I have a psi and a zeta. They're different things, trust me. So this zeta 3 is just the Riemann zeta. It's about 1.2. And the psi n is either 3/4 for fermions or 1 for bosons. Okay, it doesn't make a huge difference, but it's kind of an order one thing. The important thing here is just internal degrees of freedom times t cubed. That's your number density. Now, in the opposite limit, it turns out that you get MIT, not the school, over 2 pi to 3/2, e to the minus mi minus mu I over t, which, if you ignore the chemical potential for now, just corresponds to a Boltzmann suppression. So what this is saying is the equilibrium distribution of a very heavy particle compared to the temperature is really small because you have to pay, if you like, a standard Boltzmann penalty to create it out of the plasma. You need to sort of get lucky with a thermal excitation to make it. And at the end of the day, you have a very small density. So this means that kind of the general rule of thumb is that the density of particles in the early universe is big if the temperature is higher than their mass, and really small if the temperature is smaller than their mass, as long as they're in equilibrium. So this is the story for the number density. For the energy density, I do the same thing, but now I just put a factor of energy in with a distribution function. And this thing has a similar form to above. I won't bother going through the whole thing, but this thing looks like basically t to the 4th for temperature much, much bigger than the mass. And mass times the number density for t much, much less than the mass. And again, this makes sense. At low temperatures, basically all the energy you have for the particle is the mass of the particle itself. You don't care about its kinetic energy. Whereas at high temperatures, if your number density goes like t cubed, you expect your typical energy for this multi-relativistic particle to also be set by the temperature, so you get a T4 energy density. So this is the story. And then you can also compute pressures and whatever else you like. So this is the story in equilibrium. There's one other aspect of equilibrium that I want to get to, and that relates to these chemical potentials. So I haven't said too much about chemical potentials, but chemical potentials, if you like, are kind of knobs that you can turn to adjust number densities. So if you think of the temperature as a knob you turn to adjust the average energy, the chemical potential is similar to that, but it's a knob you turn to change number densities. Now, one thing we've assumed implicitly, or I assumed implicitly when I wrote this stuff down, is that all the particles have the same temperature here. And all the particles in the system will have the same temperature as long as they can all scatter with each other. And if you like, elastic scattering, or even inelastic scattering, is going to distribute energy from one particle to the other, and it will drive all these particles to have the same temperature, and I've assumed that implicitly here. Now, for chemical potentials control number densities, and I've introduced chemical potentials for each individual species I, but they're not all independent. And specifically, the equilibrium requirement on the chemical potentials is that if I have a reaction of the form A plus B goes to C plus D, and my system's in equilibrium with this reaction, then I get a corresponding constraint between the chemical potentials. So in full equilibrium, I go and I look at all my particles. In principle, I can give each particle a chemical potential, but then I write down all possible interactions. And when I write down all possible interactions, I get relations like these. And it turns out that at the end of the day, the only independent chemical potentials correspond to conserved charges. So I won't go through to that, but I think it's sort of intuitive. If you have a conserved charge, you can stick some amount of that charge in your system, and it's not going to change through reactions because all those reactions conserve that charge. So there's a one-to-one correspondence between independent chemical potentials in full equilibrium and conserved charges. For the standard model in equilibrium, we're going to essentially have all the chemical potentials going to 0. So one way to see that a lot of chemical potentials go to 0 is, well, first of all, vector boson chemical potentials in equilibrium go to 0. For example, a photon chemical potential goes to 0 in equilibrium because you can have processes like E plus, E minus, goes to E plus, E minus, plus you radiate off an extra photon. So if I write down chemical potentials for E plus, E minus, and E plus, E minus, and photon, here I have blah, here I have blah, and here I have mu gamma, and that forces mu gamma to be 0. So similarly, if everything's in full equilibrium, I also have 0 chemical potentials for gluons and other vector bosons. The other thing is, another process you can imagine is E plus, E minus goes to gamma gamma. So here I would have a chemical potential for E plus, and then I have my chemical potential for E minus, and this is going to be equal to twice the chemical potential of the photon, and I just argue that my photon chemical potential is 0. And this implies, and this is true more generally, that the chemical potential for an antiparticle, let's say I'll call it F bar, is equal to minus the chemical potential of the corresponding particle. Again, if you're in equilibrium, assuming they have nice annihilation channels. So it turns out that within the standard model, because we're essentially we don't assume there are any charges put in except for maybe some B minus L, to a pretty good approximation within the standard model at equilibrium, we can set all the chemical potentials to 0, and we don't have to worry about them anymore. The place where we are going to worry about chemical potentials is when we start talking about asymmetries. Because for the most part, we'll assume that relations like this hold. So I'm not going to distinguish between chemical potentials for particles versus antiparticles. I'm just going to write down the chemical potential for the particle and assume implicitly that the chemical potential for the antiparticle is just minus of that. Okay, so one thing I can get, though, with this chemical potential for the antiparticle being minus the chemical potential of the particle is I can start to look at what the number asymmetry is for a particle species, assuming it has a non-zero chemical potential. Oh, because if I wrote down this relation for this reaction, here I'm going to have mu E plus mu E minus, mu E plus mu E minus, plus mu gamma. Yeah, so it's just something is equal to 0. So, okay, so suppose I have some species m psi minus m psi bar, and I write down distribution functions for everything, and implicitly I'm going to assume that mu psi bar is minus mu psi. So I take my distribution functions, which, okay, I sadly just erased, but okay, I'm sure you all remember them, and I compute the difference between these number densities. And it turns out that what I get for what I get at high temperature is g psi over, I think it's a 6 pi x squared, mu psi t squared plus ... So the leading term at high temperature looks like this. So the leading term at high temperature for chemical potentials, let's make sure, is it squared or not? Okay, I think I forgot some pi's. Oh no, I didn't forget a pi. Never mind. So actually, there's no pi here. And then, okay. Sorry, I'm sticking this in. So this is the answer, except for bosons, there's an extra factor of 2. And that just comes from Fermi-Dirac versus Bose-Einstein, and it is just coming from doing the integrals at high temperature. On the other hand, in the opposite limit, the result for the number density is 2 hyperbolic cosine mu psi over t times what is essentially the number density of psi, which, if you recall, in the if you recall, in this limit, this thing goes like e to the minus m psi over t. So these are my expressions for the asymmetry. So not the overall number density, but the asymmetry. So the asymmetry, so just as a rule of thumb, chemical potentials compared to the temperature tend to be pretty small. And that means that for a given number density, let's say in the ultra-relativistic limit, my number density goes like t cubed, whereas my asymmetry with a non-zero chemical potential is down by a factor of chemical potential over temperature. The other thing that's useful for this is at least this leading term is linear in the chemical potential. So in other words, the asymmetry, I'll write this as the number density for the excess of particles versus antiparticles, is essentially proportional to the chemical potential. And this will be useful down the road because we're going to play some games with chemical potentials. And once we have the chemical potential, we can use this to extract number densities. Okay, so these asymmetries are going to play a big role in just a little bit. But let me just move on and I guess remind you of a few things. Using these energy densities and number densities, using these number densities and energy densities, we can write down a very simple expression for Hubble, for the Hubble expansion rate in radiation domination. So again, I think Matthias will talk about this tomorrow, but I just want to record it now just to remind you. So remember, we have essentially the Hubble relation that you have in my reduced M Planck units, 1 over 3 M Planck squared times the total energy density of the universe. So the expression for Hubble squared is total energy density over 3 M Planck squared, where M Planck is the reduced Planck mass. And in radiation domination, this row looks like a sum over all species times G times, there's a pi squared over 30. This just comes from the expression for the number density, t to the 4th. And specifically, this is dominated by particles that are light compared to the temperature, because the particles that are heavy compared to the temperature get this big exponential suppression. So the radiation density of the universe, assuming radiation dominates, which we're pretty sure it does until pretty recently, looks like this. And sometimes this is just rewritten as a pi squared over 30 G star t to the 4th, where G star is essentially a sum over the individual degrees of freedom. I forgot a fermion factor. There's an extra 7 halves for fermions versus bosons. Sorry, 7/8 versus 1 for fermions versus bosons, but okay, let's not worry about that. So this is our radiation density. And this means that Hubble, when I take this, square it, and plug it in here, during radiation domination, it goes like pi squared over 90 G star to the 1/2. Sorry, I'm running out of space. Times t squared over M Planck. So the rule of thumb for the size of Hubble during radiation domination is it's essentially t squared over the reduced Planck mass times some factor that's usually not too big. So we're going to make use of this in a second, but we see that Hubble, as the temperature falls, decreases. So this is the first thing. The second thing that we're going to make use of is entropy. So this was covered this morning, and the total entropy within an A cubed volume, so I'm going to call it entropy density times A cubed. The total entropy density within an A cubed volume is time independent for most of the evolution of the universe. So unless something weird happens, this quantity is 0. Where this entropy S thing, it's an entropy density, turns out to be G star S times an uninteresting numerical factor times T cubed. Where this G star is like the other G star, it counts the number of effective degrees of freedom. So the reason this is useful is that S times A cubed is time independent. And that means that as long as G star S doesn't change, so it does change when the temperature falls below the mass of a particle, but as long as G star S doesn't change, this relation implies that T scales essentially as 1 over A. So this expression tells us how the temperature falls as the universe expands, and we can then apply that to this, and this tells us how Hubble falls off as the universe expands. So we have our Hubble relation, we have our entropy density, and this describes the state of the universe when it's in equilibrium. So in equilibrium, I have all these nice distribution functions. I compute number densities and energy densities, and if I have chemical potentials, I can compute asymmetries. But now I want to take this and try to think about what happens beyond equilibrium. So beyond equilibrium, I have to work a bit harder. But first of all, let me say that there are two aspects to, okay, there are more than two, but for our purposes, there are effectively two aspects to equilibrium that we want to worry about. So when I say full equilibrium, what I mean is a combination of so-called kinetic equilibrium and chemical equilibrium. So kinetic equilibrium means that things scatter off each other very efficiently. And as long as things scatter off each other very efficiently, everything has the same temperature. And even better than that, everything has the same temperature, and the distribution functions are just the ones I wrote down earlier, with the same temperature for everything, but possibly different chemical potentials. Yes?
Just a short question, just to be sure, these relations are all for radiation dominated.
Yes. Yep. So for most of what we're going to care about for baryogenesis, we'll be in radiation domination. So I'm focusing on that case. Yeah. So for example, radiation domination, we know that we were radiation dominated at least at temperatures of up to 5 MeV from nucleosynthesis. And only fairly recently in the history of the universe did the radiation transfer to matter domination. And that happened at a scale factor relative to today of about 3,500. So for baryogenesis, we're going to look way, way earlier than that, where it should be a good approximation to look at mostly radiation domination. Yes?
Why would these relations still hold? Like, they just degrees of freedom drop out, right? The relations are still the same.
Oh, yeah. So these are true as long as I have those distributions I spoke of before.
Yeah, it's just the G changes.
Yes. Yeah. Yeah. Now, kinetic equilibrium, again, this is if you like, this means you transfer energy very efficiently. And this means everything has the same temperature. And kinetic equilibrium is enough to ensure that you have these very nice distribution functions that I spoke of before. On the other hand, chemical equilibrium is a thing that turns out to be a bit harder to preserve. So it's usually, for the most part, a pretty good approximation or pretty good assumption that you have kinetic equilibrium, at least as long as your temperature isn't way, way less than the mass of a particle. But for chemical equilibrium, this is the thing that tends to be harder to preserve. And chemical equilibrium is the aspect of equilibrium that tells you that you have this mu A plus mu B is equal to mu C plus mu D. So chemical equilibrium specifically refers to these relations between chemical potentials for reactions that change particle number. And what tends to happen, and the way to think about this is kinetic equilibrium is probably pretty good. Chemical equilibrium is the harder thing to preserve. And this is the thing we're going to worry about and look at primarily when we look at deviations from equilibrium. So to illustrate a deviation from equilibrium, I want to use a sort of a classic example, which is dark matter. So if we assume that dark matter has good elastic scattering with stuff, but number density changing reactions aren't so good, we'll assume that it has kinetic equilibrium, but it doesn't have chemical equilibrium. And this means that we can write these very nice distribution functions we had before, but now with time-dependent temperature and time-dependent chemical potentials that might not satisfy relations like this. So specifically, suppose I have, this is my example, suppose I have a dark matter particle that I'm going to call chi. And suppose my reaction is chi plus chi goes to standard model plus standard model. So I just have some annihilation of dark matter. Chi goes to standard model. Now, the way we describe deviations from equilibrium is through what are called Boltzmann equations. So as long as I have kinetic equilibrium, I can write my Boltzmann equations. My Boltzmann equations can be reduced to, if you like, differential equations for the evolution of number densities. So it turns out that the Boltzmann equation for dark matter chemical decoupling is given by the following form. So this turns out to be my Boltzmann equation for dark matter decoupling. Many of you will probably have seen this before, but if you haven't, don't worry about it. I'm not going to go through how one actually derives this, but you can understand the different pieces of this equation in a pretty simple way. So first of all, this sigma v is the average, by average I mean a thermal average, a thermodynamic average, annihilation cross-section. So this thing controls how likely this reaction, this chi-chi goes to standard model, is to happen. This n chi is the equilibrium number density, and specifically the equilibrium number density with mu equals to 0. So we're assuming implicitly the standard model particles have 0 chemical potential, and that means that if this reaction goes, these chemical potentials I'm assuming are 0, and that means that if this reaction is in equilibrium, the chemical potential for the chi's goes to 0 as well. So that's the equilibrium number density condition that goes into this n chi equilibrium. So what this equation says is the rate of change of the number density of my chi particle has two contributions. It has one contribution that goes like Hubble, and it has another contribution that depends on the annihilation scattering rate. So let's think about this in two limits. Suppose I turn off the scattering. If I turn off the scattering, I only have this term, and my h, if you recall, is just a dot over a, and this means that if sigma v goes to 0, my number density ends up evolving in time proportional to a to the minus 3. So what this is saying is if I don't have any annihilation, I don't have a way to get rid of the chi number density, and the chi number density then just dilutes with the expansion of spacetime. That's all that n chi proportional to a to the minus 3 says. On the other hand, suppose I have a very big annihilation cross-section. In this case, if I have a very big annihilation cross-section such that this term beats out this term, this means that if I ignore this piece and look at the stationary point of this differential equation, the stationary point of this differential equation is just the number density of chi being equal to the number density of chi equilibrium. So this Boltzmann equation is describing either the equilibrium limit of the reaction or the departure from equilibrium. So if I have a big cross-section, that corresponds to this reaction being very fast. That means I'm driven to the equilibrium number density for the chi particle. And that matches with what I would expect from chemical equilibrium, in that the chemical potential for the chi particle then matches what I would have in equilibrium, which just corresponds to a chemical potential of 0 in this case. On the other hand, if the reaction is slow, if I turn off the reaction, I don't follow the equilibrium density. Instead, I just dilute with the expansion of spacetime. So the interesting part, though, is the limit between these two things. So the interesting thing is the limit between these two behaviors. And the limit between these two behaviors corresponds to when these two terms become of similar size. So if this piece wins, I get this behavior. If this piece wins, I get this behavior. And the thing to compare is, at the end of the day, the rate of Hubble. So the rate of Hubble is what goes into here versus the thing that goes into here, which is roughly the size of this. If you think about canceling off one factor of the number density, if I'm close to equilibrium, I'm going to track the equilibrium pretty closely as long as the combination of cross-section times equilibrium number density is much bigger than Hubble. So what ends up happening, though, and this is the standard freeze-out paradigm, is as a function of time. And you can also think of, well, actually, instead of time, I'm going to use 1 over temperature. As a function of 1 over temperature, what happens is, here's 1 over the mass of chi. What happens is, when I write my, if I normalize to t cubed, at high temperatures, n chi over t cubed is just some constant of order 1. On the other hand, as the temperature approaches the mass, and I stay in equilibrium, my equilibrium number density is going to become Boltzmann suppressed, and I'm going to fall off. And typically, in the case of dark matter, what happens is you track equilibrium for a while until this piece gets small because of the Boltzmann suppression, and this combination becomes of the same size as Hubble, and you then deviate away from equilibrium, and you end up with n chi proportional to a to the minus cubed, which is also how the temperature, which is also how the temperature expands, and you have some deviation from equilibrium. So this is my actual n chi. This is my n chi equilibrium, and this is an example of departure from thermodynamic equilibrium. And it's an example specifically of departure from chemical equilibrium, in that the corresponding elastic scattering rate that keeps the kinetic equilibrium, instead of having the chi number density, I'm going to have something like a standard model particle number density. So this is just a very simple example of departure from chemical equilibrium. We're going to look at we're going to look at similar ideas, maybe not quite exactly this, but the rule of thumb is, for a particular reaction to be effective, to be active at equilibrating the system, the effective rate of the reaction should be greater than Hubble. So if I want to enforce a chemical equilibrium implied by a particular reaction, I look at its rate, its effective rate, I compare it to Hubble, and the rule of thumb is, if that rate is a lot bigger than Hubble, then this relation between the chemical potentials is a good one. And I'm in chemical equilibrium in the sense that this relation holds for that particular reaction. On the other hand, if the rate of the reaction is less than Hubble, all bets are off, and chances are I don't track, I can no longer apply this relation between chemical potentials. Okay, so a really important reaction we're going to look at for baryogenesis is these Sphaleron transitions. So if you recall, the effective rate for Sphaleron transitions, before I had the rate per unit volume, if I normalize this to the rate, if I normalize this to just the rate, not the rate per unit volume, but the rate, my Sphaleron rates look something like this. They go roughly like alpha weak to the fourth times the temperature at very high temperatures, well above the weak scale. And they go like this exponentially suppressed thing at temperatures below the weak scale. So I have this, and my Sphaleron reaction, my Sphaleron reaction changes B plus L by 3 units for each reaction. So for each Sphaleron jump, I change B plus L by 3 units. And specifically, what I change when I change B plus L corresponds to the operator QQQL cubed, where I have a factor of this for each of the 3 generations. So the corresponding relation that I get from Sphalerons, the chemical potential relation implied by Sphalerons, is that I have I have a sum over generations over the 3 generations. Because it corresponds to this operator with 3 left-handed quarks and 1 left-handed lepton, the relation I would apply for Sphalerons being in equilibrium looks like this. So I have 3 quarks and 1 lepton essentially going into nothing in a Sphaleron transition, or back and forth. I sum that over generations, and this is the chemical potential relation implied by Sphalerons being active. But the thing to check for whether Sphalerons are active or not is to compare this rate to Hubble. And Hubble, assuming radiation domination, goes like T squared over M Planck. Yeah, in question.
I mean, what is the separation scale of this operator? This is high dimension.
Sorry, the separation scale of.
When you write this operator in Lagrangian, so when you use the separate scale, because it's not dimension 4.
Yeah, so there's not a nice, okay, so at high temperatures, there's not a nice way to write it as an effective operator. At low temperatures, well below the weak scale, you can write it as an effective operator that looks like this, with something like 1 over mw to however many powers you need to make this dimension 4. It's like 18 or something. And then plus, you also get an exponential suppression. So
Weak suppressed.
yeah, but this only makes sense below the weak scale. But even well above the weak scale, the reaction is still QQQL for each generation, essentially going to nothing. And in all possible crosses of that. So this is the chemical potential relation you get from the Sphalerons being active. Now the thing we have to check is whether the Sphalerons are active by comparing their rates to Hubble. And what you see is if I go to very high temperatures, the Hubble is going to increase faster than my high temperature Sphaleron rate. So Hubble is going to go like T squared, where the Sphalerons are going like T. And I have a lot of coupling suppression. And the upshot is that Sphalerons turn on and turn off at high and low temperatures. So what I mean by this is if we plot the rate as a function of 1 over temperature, we have some line like this that corresponds to the Hubble rate. So it falls off like it falls off like T squared. So this is going as 1 over T. On the other hand, if I look at my Sphaleron rate is going to fall off less quickly, well above the weak scale. So I'm going to make this my weak scale. So my Sphaleron rate, let me get some nice colorful chalk. My Sphaleron rate is going to fall off more flatly than the Hubble rate until I hit the weak scale, at which point I transition from this T behavior to the exponentially suppressed behavior. So this thing is going to turn over and then fall off the map very quickly. So the rule of thumb for a reaction to be relevant, for a reaction to be in equilibrium, is that the rate should be larger than Hubble. So in other words, this region corresponds to sphalerons being in equilibrium. And if you sit down and you work out the numbers carefully, what you find is this corresponds to a range of about 132 GeV up to about 10 to the 12 GeV. So on a cosmological scale, in terms of equilibrating B plus L number, sphalerons are really fast. So sphalerons are active. They equilibrate your system. In this sense of equating chemical potentials, these chemical potentials to zero, for temperatures between about 130 GeV and 10 to the 12 GeV. So we're going to make use of this for mechanisms of baryogenesis, because this is going to give us a way to violate baryon number that's safe, and that we can have all this baryon number in the early universe, which is what we need for baryogenesis, but we're not going to have to worry about protons falling apart today, which is good because I don't want to explode. Okay. So I'm going to change gears a bit, and I want to try to illustrate how these Sphaleron conditions are realized within an explicit mechanism of baryogenesis. And the first mechanism of baryogenesis I want to talk about is leptogenesis. So, okay, I'll leave this up for now and start over here. So leptogenesis, the idea of leptogenesis is that you have, okay, I'll get to this in a second, but you have heavy right-handed neutrinos that decay out of equilibrium. And these heavy right-handed neutrinos, in their decays, can produce a net lepton number. Now, this net lepton number is then taken up by the sphalerons and turned into partially a baryon number. And the baryons left over from this at the end of the day are what we see today. And one of the very nice things about leptogenesis, or at least some realizations of leptogenesis, is that there's a very nice connection between the baryon asymmetry we see today and the origin of lepton masses. So you'll hear a lot about neutrinos later in this course, but one thing we know about neutrinos is they oscillate. And the fact that we see them oscillating corresponds to them having non-zero masses. The oscillations correspond to a mismatch between what are called flavor eigenstates. So whenever you produce a neutrino, it comes in conjunction with a charged lepton. So we see the charged lepton, and that tells us what the so-called flavor state is. But the mass eigenstates of the neutrinos corresponding to their energy propagation eigenstates don't quite match up with the flavor states. And because of that, you get this phenomenon of neutrino oscillations, but it requires that neutrinos have masses. Now, if you recall, in the standard model, we just don't have neutrino masses at all. So at the minimal or normalizable level, there's no neutrino mass in the standard model, so we need new stuff beyond the standard model to explain the neutrino masses. The easiest way to generate a neutrino mass is to add a new so-called right-handed neutrino to the standard model. So a right-handed neutrino has SU3, SU2, U1 charges of, it's a singlet under SU3, singlet under SU2, and has zero hypercharge. So it's a total gauge singlet. And the minimal interaction you can write down that generates neutrino masses is, let me just get my notation right, is lambda is this combination. So I've got my Higgs field talking to the standard left-handed lepton doublet, and it's connected through, I'm writing this as a dot, and this means that I have epsilon AB, HA, LB. I'm connecting up the SU2 components with an antisymmetric epsilon tensor. And it turns out that this gives you a gauge invariant combination for SU2 groups. So this is a gauge invariant thing. The hypercharge of my Higgs cancels out the hypercharge of this. So lepton has -1/2, Higgs has +1/2. This has nothing. So this is gauge invariant. And after electroweak symmetry breaking, I turn on the Higgs valve, and it turns out that this predicts a neutrino mass that goes like lambda V, where lambda is Yukawa coupling and V is the Higgs expectation value. And based on what we know about neutrino oscillations and cosmological limits on neutrino masses, the standard model-like neutrinos have to have masses less than about 0.1 eV. So if I want to get less than 0.1 eV masses with just a regular old Yukawa coupling, this coupling has to be really, really small as well. So there's nothing wrong with that coupling being very small. It's technically natural. But okay, you might wonder, okay, why is this coupling so small? This bugged people for a long time. So one way to get very small neutrino masses with bigger Yukawa couplings is to add a mass term for the right-handed neutrino. So if I take my L and I add to it a mass term for the right-handed neutrinos. So I'm going to assume implicitly that it's a right-handed, it's a diagonal mass. If I had a mass term for the right-handed neutrinos, what I get now is my mass matrix for the neutrino states now has this contribution, and it has a contribution from electroweak symmetry breaking. And what I get for my mass matrix is something that looks like lambda v, mn is my mass matrix. And if you diagonalize your 2 by 2 matrix, what you find as mass eigenvalues are there's a light eigenvalue and a heavy eigenvalue. The light eigenvalue looks like this. The heavy mass eigenvalue is basically just mn. So in this setup, where I have in mind that this mn is really, really big compared to the off-diagonal entries, what I get for my mass matrices are, well, a big value, and the big value is mostly the singlet state. And then I get really little values that look like lambda squared v squared over this big mass. So the upshot is that if you happen to be bothered by very small Yukawa couplings, for one reason or another, you can get around that by putting in a heavy mass for the fermion, for this new right-handed fermion. And in particular, if you want to get like a 0.1 eV neutrino mass, this thing of about 10 to the 14 GeV and a Yukawa coupling of order 1 gives you about 0.1 eV. So this is called the seesaw, and specifically it's called the type 1 seesaw. And one nice thing about this type 1 seesaw is that it gives also a very nice mechanism for baryogenesis called leptogenesis. So I should say that there are lots of different ways to make leptogenesis happen. I'm going to look at the realization of leptogenesis in some sense in this minimal type 1 model, and this is the case that's been studied in the most detail. Okay, actually one other comment in passing is that the standard model, the renormalizable level, doesn't have any neutrino masses. This theory, if I integrate out the heavy neutrino, generates a dimension 5 operator involving only standard model fields. So if I integrate out this operator, I get something that looks like L dot H squared times 1 over mn. And this dimension 5 operator involves only standard model fields and generates neutrino masses on its own. And it generates light neutrino masses in that the values I would get from this match up with the seesaw by diagonalizing the mass matrix. Just a comment in passing. Okay, so in any case, we have this type 1 seesaw, and we want to do baryogenesis with it. So we need 3 things for baryogenesis. The first is baryon number violation. So we have that from the Sphalerons. But this theory also gives you something more. It gives you lepton number violation explicitly. And what I mean by this is we know that this lepton has lepton number +1. And that means that our right-handed neutrino should also have lepton number +1 for this thing to be invariant. But the structure of this mass term involves this C corresponds to the charge conjugate of n bar. And in terms of lepton number, this operator has lepton number +1, but it turns out that this n bar C also has lepton number +1. So the C is like a conjugation, so you can think of this thing as conjugating twice. So this piece has lepton number 1, this thing has lepton number 1, and that means I get 1 + 1, which is 2 and not 0, implying that this operator combined with this operator violates lepton number explicitly. So this theory also has lepton number on top of baryon number violation, and we're going to make use of this in a minute. The third thing, or the second ingredient beyond baryon and lepton number violation is C and CP violation. So we already have C and CP violation in the standard model, but we can have additional C and CP violation in this theory if we have enough generations of the right-handed leptons. So it turns out that to get a non-removable phase, you need at least 2 generations of the right-handed neutrinos. I'm going to assume 3 just for symmetry with a standard model. So we have C and CP violation, and in fact, new sources of C and CP violation from this coupling. We have lepton number violation from this coupling. We have baryon number violation from the Sphalerons. And the last thing we need is departure from equilibrium. So I'll come back to the departure from equilibrium in a second, but I want to get back to slightly more about the about how C and CP violation come in for generating the asymmetry. Okay, so if I look at the way the right-handed neutrino in this theory decays, it has, oh, question?
In this CK matrix, you need at least 3 generations to
Mhm.
get the violating phase. Here you said you needed them 2. Is that because it's an
I think so. I haven't sat down and done the counting, but I think that's right. I know 1 doesn't work. 1 generation also doesn't work for making all the neutrinos massive. So you can't generate the neutrino mixing matrix with only 1 generation of right-handed neutrinos. So you need at least 2. I know you also need at least 2 to get a CP violating phase. I suspect the answer is related to the Majorana mass, because with the Majorana mass, you essentially can't rephase the NR independently. Because if I rephase the NR, I also mess up the other thing. Yeah. Okay, so for C and CP violation, we can have this from the lambda A. And the way C and CP violation is going to come in is in a decay asymmetry. So the structure of this mass implies that the right-handed neutrino is a Majorana fermion, which means it doesn't have a distinct antiparticle. And it turns out that I can have my right-handed neutrino decay in 2 ways. I can have it decay to LH, or I can have it decay to L bar H dagger. And I'm going to put family indices, so I'm going to call this I, and I'm going to call that A. So A labels the different standard model lepton generations, and I labels 1 through 3 of the heavy right-handed neutrinos. And with C and CP violation, I can get slightly different partial widths to this channel versus this channel. And computing this is a little bit tricky. So for the decay, actually, sorry. So if I look at the matrix element, for this decay, it has a tree level contribution. And the tree level contribution can involve these CP violating phases, these in general complex lambda AI couplings. So the matrix element for the amplitude for this thing, schematically, is going to have something that goes like lambda with some indices attached to it. So it's going to look something like lambda IA. And then if I look at the same thing for this for this conjugate reaction, I'm going to have something that looks like lambda AI star. So this is starting to look pretty good. I've got a phase difference, because I have non-removable phases. But when I actually compute the decay rate, what I do is I take this, I square it, and then I sum over final momenta. And obviously, if I take the modulus squared of this, I'm going to get the same thing as the modulus squared of this. So just because I have a CP violating complex coupling doesn't mean that, at least at this tree level thing, that I actually get a decay asymmetry between this channel versus this channel. To get a decay asymmetry, I have to work a little bit harder. I have to go beyond tree level, and I have to include higher order diagrams. So the tree level diagram is just this. Here's NR, L, H. But beyond tree level, I've got extra contributions. And the extra contributions have the following form. Where okay, my arrows probably aren't right, but so I get extra contributions like this, and then I can also get extra vertex corrections. So actually, sorry, this is the Higgs here. N L H So if I go beyond tree level, I have extra contributions that have now multiple powers of the coupling. So instead of having one power of the coupling, I would have a tree level. I now get extra powers of the coupling from this vertex, and this vertex, and this vertex. So beyond tree level, the next contribution has 3 powers of the coupling. And these extra powers of the coupling that come in can correspond to different heavy neutrino varieties and different regular lepton flavors. So the next thing I have is M goes like, I've got my lambda AI and lambda AI squared. And then my next piece is going to look like a lambda, lambda, lambda with all kinds of funny contraction stuff in between that I don't want to get into. And then there's going to be an extra contribution from the loop factor. So I'm going to call this C1. And then similarly, for the conjugate thing, I get something similar here, but now starred. So I get the complex conjugate, and I'm going to get something I'm going to call C1 bar. So now I look at this, and I look at this, and I square this, and I square this, and oops. What I find is if I square this and I square this, I'm going to get the same answer if C1 bar is equal to C1 star. So what I need to get non-trivial CP violation is C1 bar different from C1 star. So specifically, if I look at the difference between M squared and the conjugate M bar squared, it turns out that this thing is proportional to minus 4 times the imaginary part of essentially a combination that looks like lambda the fourth with all kinds of flavor indices mixing together. It's going to come from a cross term between this piece and this piece times the imaginary part of C0. Okay, actually, sorry. Let me just correct something. Sorry, I'm goofing at my notation. Okay, so for the most part, this thing turns out to be the same as this, even though I have complex conjugates here. So if this thing were real, this imaginary part would vanish, and I'd be hosed. So I'm implicitly putting all the conjugation stuff into this piece rather than this piece. But it turns out that this piece can have a non-zero imaginary part in a way that respects CP. And you can get non-zero imaginary parts in amplitudes that respect CP if you have intermediate particles going on shell. So roughly, if these states are heavy, I can have these states go on shell as intermediate states. And it turns out that through unitarity of the S matrix, you can relate the imaginary part of these loop diagrams to essentially tree-level diagrams where I cut through the intermediate states that go on shell. So there's a sneaky unitarity trick to do this. And the upshot is you can show that as long as I have intermediate particles going on shell, this imaginary part of C1 is non-zero. So I have more details in my notes. I don't want to go into more detail here because I'm just going to goof it up. But the result at the end of the day for the CPA symmetry is we have a CPA symmetry, and I'm going to call it epsilon 1. And I'm going to focus specifically on the CPA symmetry generated by the lightest of the heavy right-handed neutrinos. And the result for this is, okay, it's kind of a messy expression, but the asymmetry into flavor A goes like, okay, well, first of all, this is defined as the difference in the decay to particles versus decay to antiparticles divided by the sum of the decay rates. So this is our so-called decay asymmetry. So it's a difference in the rates normalized to the sum of the rates. And this thing goes like 1 over 8 pi, 1 over lambda lambda 1 1 times a sum over I of okay, so I'll only write one term, but it's an imaginary part that involves 4 couplings. Okay, so you can look at my notes for the precise expression, but I have some loop function piece. I have something that depends on the couplings, and specifically, it's a combination of those couplings that involves a phase that I can't get rid of through field redefinitions, and then the rest is just normalization factors. So what I can get at the end of the day is a decay asymmetry in the sense that my right-handed neutrino, one can decay slightly more into leptons than anti-leptons. So the things I need from this are lepton violation, and I have this already from just the fact that my right-handed neutrino is Majorana, and it can decay to a particle or an antiparticle with different lepton numbers. But the other things I need to get for this non-zero asymmetry is CP violation, and that corresponds to this thing being non-zero. But to get the CP violation to actually be physically relevant, I have to work harder than just tree level. So remember, if I just stopped at tree level, I get m squared equals m bar squared, and I wouldn't get anything interesting. Instead, I need to go to at least one loop and take into account these intermediate on-shell states. But when I do, I get a non-zero result of the following form. So I have this decay asymmetry. I have heavy right-handed neutrinos decaying a little bit into a little bit more into leptons versus anti-leptons. And the way leptogenesis works, and I'll finish this up, actually I guess not tomorrow, on Thursday. The way leptogenesis works is, suppose I have my N1 heavy fermion decaying way out of equilibrium. So in other words, suppose my N1 density is much bigger than the equilibrium density. And suppose it decays at some temperature that's way below the mass. So I have some N1s floating around with a much larger than equilibrium density. They just kind of hang around until they decay. When they decay, they're going to produce slightly more leptons than anti-leptons, and that creates a lepton asymmetry. And as long as this decay happens out of equilibrium, that lepton asymmetry is going to be frozen in. There won't be any processes that can wash it out. That lepton asymmetry is then going to be eaten up or partially eaten up by the sphalerons that will convert some of this lepton asymmetry to a baryon asymmetry, and that will give us the baryons we see today. So let me wrap it up here. I'll finish this off tomorrow, but if you have questions, I'm around. Thanks.